So, welcome everybody. Welcome to another GEC webinar. Today, as our guest, we have Riccardo Chebac. I hope I pronounced it right. And today he will talk to us about the future of nuclear, SMR, and Generation 4. Please, the podium is yours. Riccardo, you can take us into the world of nuclear.
Thank you, Lina. And thank you all for coming in. So first of all, let me present myself. I'm Riccardo Chebac. I'm currently at my last month of Ph.D. in nuclear engineering at Politecnico di Milano. I've been a researcher for the past 3 years. I've also worked at the OECD NEA and the Radioactive Waste Management and Decommissioning Division. My research is basically on graphite moderated reactors dismantling, specifically on the robotics side, so how to extract graphite blocks, and also on the decontamination side. The decontamination side has been a project between Politecnico di Milano and University of California, Berkeley, where we basically tried and succeeded to a certain extent in decontaminating graphite using advanced molten salt techniques. And today I'll talk a little bit about the future of nuclear, SMR and Generation 4. Now, nuclear has become quite a hot topic recently because apparently it has come back in the highlights of a possible solution for the energy crisis that we are facing. But before going into the interesting part, I would like to play in the field and basically explain to everyone how a nuclear reactor works. This can help you also then understand why these new technologies are specifically extremely interesting. A nuclear reactor is nothing more than the most complicated boiler ever built by human. What this means is it doesn't work differently from a coal-fired plant mostly, or any type of steam cycle plant per se. What we do is we heat water, the steam, the superheated steam goes into a turbine, the turbine then rotates an alternator that then produces current. Now, the difference between us and any type of every other type of steam plant is how we produce the heat to then produce the steam. And this is done by nuclear reactions, of course. Specifically, what is usually done is by fissioning uranium, specifically an isotope of uranium called uranium-235. This is around 0.7% of the uranium available on Earth. And the interesting part is that by utilizing nuclear processes instead of chemical processes, the energy that we can get as an output is millions of times greater than what we could have from a chemical process. Just to give you an example, usually one uranium pellet, you can see it's extremely small, usually produces the same amount of energy that comes from 17,000 cubic feet of natural gas, around 120 gallons of oil, or roughly 1 ton of coal. So this is what we call energy density. So basically how much punch, we could say, we get from a certain mass. But there's also another advantage. See, nuclear is the only source that is both extremely energy dense and power dense. What it means, let's say, for example, we take into consideration renewables. The definition of renewable energy is an energy source that renews constantly, or basically that the renewal rate is far faster than the consumption rate that we have. Generally, this is true, but it considers only the primary source, while the secondary source, which means basically how much land we need to use, how much materials we need to use to create the system that then produces energy, is extremely high. This given that any type of renewable energy has extremely low power density. Power density, therefore, we can correlate it to the use of the secondary materials and not the primary energy source. What this correlates to? This correlates to having, for example, a nuclear plant in Belgium, or this is just in general, it's just Belgium for this picture, requires 285 times less land than solar and 412 times less area than wind. As you can see on the right-hand side, we can see how this relates or correlates to the amount of resources needed to produce a plant. And as you can see, nuclear and gas even more use extremely low resources in this case, and this is extremely important. Now, remember, we're now talking about the future of nuclear, specifically the short and long-term future, and this is what good investors usually should do. Now, what do we have in the horizon? The first of all is SMRs. Now, I wanted to start with SMR. At first, I was asked to talk about small modular reactors, I will focus more on generation 4 for one simple reason. SMRs are not, I wouldn't say they're a reactor, but they're more of a design philosophy, which can be applied to every reactor in existence, both modern reactors and advanced reactors. So once we have grasped the concept of what an SMR is and what could be the advantages of an SMR, then we can move to understanding instead the advantages of advanced reactors, which could be or could not be SMRs depending. So SMR is just, as I said, a design philosophy. The definition is any reactor that produces less than 300 megawatts electric. The second point is that it's modular. Modularity means having limited on-site preparation. Most of these SMRs are probably will be produced in factory and then be shipped. This should technically reduce cost and time. And one other important part is that technically they will have lower capital investment and therefore lower financial risk. And also being small has the advantage of having siting flexibility. So we can put these type of reactors where we couldn't be do that before. And third and last, they have enhanced safety compared to their larger cousins. This is mainly due to one reason, which is the decay heat from the reactor. So for the non-experts, when we shut down a reactor, we then have what is called the decay heat, which is basically a heat coming from the decay process of the fission products that has to be cooled in the subsequent weeks and first months after shutdown. Now, the smaller the reactor, the smaller is the decay heat at shutdown. The smaller it is, the easier it is to control, especially in case of an accident. Therefore, that's why they're usually safer. And also, being smaller enables the possibility to use enhanced safety features, especially passive safety features, which are much better suited to increase safety and reliability. Now, let's say that usually reactors are big because they follow what is basically called the economies of scale. So the larger a system becomes, usually the more economic it is. So SMRs, to actually become more profitable, have to leverage other advantages, which are, as I said, modularization. Modularization factory build usually is one of the main core components that actually manages to reduce cost quite a bit. Design simplification, as I said also before, passive safety systems usually are easier to build, are less complex, and therefore this also reduces. Then there is standardization and harmonization. These two are usually kept separate, but I would keep them together in the sense that one doesn't exist without the other. Harmonization means, usually broadly speaking, on a regulation standpoint. And why is it important? It's important because standardization on a wide scale application cannot happen without regulation harmonization. How this happens, this is a little bit of wishful thinking. We have to create a sort of regulation that is harmonized throughout the industry worldwide. And that's probably how these reactors could become more economical. Now, if you listen correctly, I said could, because to date, we do not have enough economical data to back up this statement. Could be, could not. The potentials are definitely there, but there's more to work on. Now that we understand that the SMRs are technically just a design philosophy, I would like to go a little bit more into the interesting part, which is the generation 4. The generation 4 is basically a new, I would say new concepts, but most of these concepts actually come from the 60s and 50s, but nonetheless, I would say commercially they're new concepts. If you look at the evolution of reactors until generation 3 and generation 3 plus, we just had an evolutionary design approach. So we have the same reactor, more or less, which is the light water reactor, usually in the form of pressurized water reactors and boiling water reactors, and they have been evolved and optimized throughout the years. Now we're basically shifting the paradigm of how nuclear reactors work. So this is what we call passing from an evolutionary to a revolutionary approach. What are the main goals of generation 4 reactors? Now I will talk through all of these. Bear in mind that all of these reactors will excel in some of them and not so much in others, and so on. So it's not like there is one solution that fits all of these points. And these points are waste minimization. Some of these reactors, especially the ones that have high burnups and fast neutron fluences, are capable of, first of all, producing less nuclear waste. Usually the nuclear waste that comes out of the reactor is just fission products and activation products that usually last less than 300 years. Then effective fuel utilization. So if you remember what I told you before, uranium-235 is roughly 0.7% of the uranium available. Fast spectrum reactors can use the remaining, let's say, 99.3%, which is the uranium-238, as well as also other fuels like plutonium, which is also partially used in modern reactors, and also, for example, thorium. Higher safety. The higher safety is an interesting advantage that, of course, then depend on the reactor. The reason why they have higher safety, I will go into details on each reactor later. A lot of interesting design approaches. Then one of the main points I would like to keep for later is higher efficiencies of the plant. So one thing that all these reactors have in common is a higher temperature output. Consider that modern reactors reach usually 330 degrees of the superheated steam. And the efficiencies of the plant are around 30, 35, depending on the place. And those are quite low. We don't really care that much about the efficiency because the fuel is very cheap. But even though the efficiency per se is not what we're interested in, the higher temperatures that we can reach are extremely interesting for a number of reasons that I will keep for later. Now, this one, the point I'm about to say, at the moment that's one thing they're trying to go for. There's no backing up that right now. Again, more attractive economics. I'm usually very skeptical when we talk about economics because until we have a large data set where we can make our estimates on, it's very difficult to actually say. Honestly, working with some of them, at the moment, light water reactors are much more economic. That being said, there are some advantages that can be brought into future. Lower financial risks. Again, this is more related maybe to the modularity, but it has to be shown. And also proliferation resistant. So basically, by better using the fuel, especially burning the plutonium, it's much safer because we do not produce weapon-grade material. That's a good point, a good selling point, especially for reactors like the HDGR that have triso fuel. In this case, it's basically, I wouldn't say impossible, but very hard to separate the plutonium from the rest, and therefore it's not an attractive solution for proliferation. Now, before going on each reactor on each of these points, I would like to highlight some things, especially safety. We talk about these reactors being safer than the reactors that we have to date. Now, this is another thing that could be the case. We do not have, it's most likely, but just to put it into perspective, to date, nuclear is already one of the safest energy forms available. It's comparable to wind and solar. And then, of course, it's also green. It produces even less CO2. Another metric that I always like to show is that the probability of having a lethal accident coming from a nuclear-related accident is lower than the probability of us being struck by a lightning. So yes, true. Maybe new reactors are safer, but is it really what we should be going for? I mean, it's difficult to say, but as you can see, the numbers are already saying these reactors are already extremely safe as they are. That being said, another one is waste minimization. Now, it's true. Modern and advanced reactors can produce waste that is extremely lower in radiotoxicity, especially in lower terms and timescales, especially 300 years. Nonetheless, I want to show you how much is the actual nuclear waste, the high-level nuclear waste that we are producing. This is a comparison. You see, the first big ball is the industrial waste usually produced by the European Union each year. That's about 1 billion meters cubed. Of that, the high-level waste, radioactive waste that we produce is 500 meters cubed each year for the European Union. What does that mean? It means that if we just use nuclear for our entire life, each person would produce around 1 soda can of high-level waste. Just to give you a perspective, this is went too far. This is how small the can usually will be, 33 centiliters. So what the advanced reactors would be doing is going to burn this stuff. It's not a lot. It's still better if we can solve it, but as you can see, this is not the main issue. This is just to show you where advanced reactors can excel. So of all the nuclear waste produced, only 3% is the high-level waste that lasts for millions of years. That's the high-level waste. Then there's the intermediate level waste and the low-level waste. Now, for the intermediate and low-level waste, regardless of there being nuclear reactors or not, would still be produced by each nation, because this also comes from refineries, from rare earth minings, from medicine. So hospitals produce them a lot. So these are, I would say, the big problem. The big problem is the 3% high-level waste. It's the smallest in volume, but holds, if I recall correctly, around 99% of the overall radioactivity. The 3%, as you can see on the right, can last millions of years, depending on the burn-up, depending on a series of things. But if we use advanced reactors with a continuous recycling approach, then we can move from the red line to the green line, and that's the big advantage. But as you can see, even if we're capable of minimizing waste, I've basically tried showing you that the waste is not really the problem. Safety is not really the problem. So one could ask myself, but Riccardo, why do we then want advanced generation reactors? What are they really excelling at? And remember what I told you before, temperature. Why is it temperature so important? And temperature is important because of this. Now, this is basically how the entire CO2 production worldwide is divided in. You can see there is a 18% that's coming from agriculture and land use, 3.2% that is waste, 5.2% which is industry, and 73.2% which is energy. Now, I said energy, I didn't say electricity. And this is the main point, because if you see, the electricity is the minority of this 73%. The rest is transport and is energy used in industry. And this is what I want to, because the energy used in industry is mostly not electricity, but heat. And heat that usually is used at high temperatures. So the real, I would say, business case, pass me the term, for generation for reactors is not even electricity production. In some cases, yes, but it's mostly for producing heat at high temperature for industrial applications. As you can see here, there is basically this graph is comparing the various industrial processes and the heat required. And underneath, you can see different reactor technologies, from light water reactor, then you can see liquid metal reactors, HTGRs, and so on, and molten salts and gas fast reactors. And you can see their temperature ranges. What this basically means is that if you see the top line and the lower line, the top blue lines, you can compare them to a reactor and see which reactor is suitable for which industry. And this is one of the most important parts. Another important part, specifically then for MSRs, is that some of these reactors will produce electricity in a more flexible manner. And this is extremely important for these, let's say, I would say, very interconnected grids that we're going for, highly penetrated by renewable energies. Having a very flexible reactor that is still extremely economically advantageous in flexible terms is what we need for this type of system. But here's basically what I'm trying to say. These reactors are important for industry, also for transport. Like, some of these reactors are extremely interesting, for example, for ship propulsions. And again, as I said, another important part is that they're extremely flexible. This means that reactors of this type, I also actually, my master's thesis was on that. Advanced reactors are more flexible in electricity production. And this enables a very interconnected grid that are usually called hybrid systems, where you have reactors that are extremely flexible and that can produce also steam, or in general process heat at high temperatures, that enable a very intertwined grid that can then produce goods like desalinated water, hydrogen, biofuel, and so on. We can also have district heating, and we also have at the same time grid frequency stabilization. If you're curious about more in-depth analysis, I can also send you my thesis or other literature review regarding that. But now that we talked about that, I will talk to you a little bit about all the generation for reactors, their advantages and disadvantages. And I will also tell you which one, for me, are the best ones. The first one is the sodium-cooled fast reactor. This is, I would say, one of the reactors that is, I wouldn't say commercially available, but has been built quite a fair bit. The picture on the right-hand side, the one right-hand side lower, that is the BN800, which is a Russian reactor that's currently being used. Sorry, BN600, not 800. So it's a reactor that has been working a lot. The smaller version, the BN350, if I recall correctly, has also been used to desalinate water. So this is quite an impressive feat. Characteristics of this reactor is that it's a liquid metal reactor. What it means is that the coolant is a liquid metal. And it's a fast spectrum reactors. No, I didn't go into details about the neutronics, but there are usually two types of reactors: thermal reactors and fast reactors. The thermal reactors are basically the ones we have today, most of them, which are basically they utilize a moderator to slow down neutrons and increase the probability of fission. And then there are the fast reactors. These reactors do not slow down neutrons, so it's a little bit more complex to keep the fission reaction going. But the advantage is that the neutrons are extremely high in energy. And this basically means that they can destroy, for example, fissionable isotopes as uranium-238 and have better fuel utilization. So if done correctly, these reactors can burn basically everything. This reactor specifically has quite high operating temperatures, around 550 to 600 degrees. And it has a high breeding ratio. Now, fast reactors are capable of producing more fuel than what they're actually using, which means that you can basically create an economy where reactors actually produce fuel for new reactors and so on. This is actually quite interesting. It's a bit complex as a concept, but very interesting. And also, again, since it's in a fast spectrum, has enhanced fuel utilization and can reduce long-lived waste. There was one of these reactors, the Super Phoenix in France, that, if I could recall correctly, has burnt around 25 tons of plutonium during its operating life. One drawback from this reactor is that sodium is highly reactive. Specifically with water and air, it can burn and explode. So this is quite an issue. So as you can see, one way to make it safer is that instead of having the reactor immediately connected with... Do I have a pointer? I don't know if I have the possibility of pointing. Maybe not. Let me see. Aha, yes, okay, sorry. So usually this is the reactor core, and you have the steam generator. Usually in like light water reactors, the steam generators goes directly to the turbine. As you see instead here, you have an intermediate steam generator that basically is radioactive sodium, non-radioactive sodium, and then steam generator. This increases the safety quite drastically and basically reduces all the problematics. Another molten metal fast reactor is the lead-cooled. This one has been used a lot by Russia, again, specifically in submarines, and is now also being built again in Russia, another prototype, which is the Brest OD300. This uses molten lead or lead bismuth eutectic as a coolant. Actually, now it's more and more going towards only lead. The advantages of using lead bismuth is that you have a lower melting temperature, so it's easier to control. The disadvantage of lead bismuth is that you produce around 20,000 times more polonium-210 compared to pure lead. And this is quite a issue from a radiation perspective, a radiation protection perspective. Therefore, for radiation protection and I would say waste management issues, more and more reactor vendors of reactors of these types are moving towards lead. Again, this is also fast neutrons, so basically nothing more to add compared to what I said before about sodium. And again, the temperature ranges are similar to that of sodium. They can also advanced lead reactors that are being designed can also go up to 800, but there has to be quite a bit of improvement on the materials science side. Lead is probably it's one of the best coolants we have. Good thermal inertia, so it's also extremely good for like load following. It has one of the best burn-ups, specifically because you can have a harder spectrum of neutrons compared to sodium. It's extremely safe. Lead is inert and also uses natural circulation. So this is a really good and interesting device. And it's really good for breeding and transmutation. Now, one of the reasons lead is not as used to date as sodium is that sodium is not as erosive and corrosive as lead. So there are some corrosion and erosion issues that still have to be dealt with and also oxygen control to actually enable this reactor to reach commercial availability. Specifically, also oxygen control is a big one. Very small and trace amounts of oxygen are enough to create what are basically oxides that can damage the whole system. So that's one thing that's being worked on. Then there is the high temperature gas reactor. These ones have been designed quite a few and operated also quite a few in the past. There was one that recently has been turned on and connected to the grid, which is the HTRPM in China. It started operations on the 20th of December 2022, and full power. It was on the 20th. It was connected to the grid, and 22nd, I think it was full power. This is another thermal reactor instead. So it utilizes a moderator, which is graphite. Basically, all my research is revolving around graphite somehow. Utilizes helium as a coolant. Here I wrote it reaches extremely high temperatures. It says 700. We can go even higher. We can go around 900 to 1000 degrees. This is one of the safest reactors because it utilizes what is called trisofuel particles. I will not go too deep into it. If you're curious, we can talk about it later. But basically, these type of particles are extremely robust and are basically accident tolerant. Consider that one of the main metrics used to identify the safetiness of a reactor is what is called core damage frequency. Core damage frequency for TRISO is 0. It is the only reactor that has this type of feature, and it's impressive. So these are one of the best for high application process, especially for steel making and glass making, and also hydrogen. Extremely good for cogeneration also. And what else? Anything else to say? They have also extremely good burn-ups, so also they're very efficient in using fuel. And another very good advantage is that theoretically, the fuel as it is can be also disposed of if we do not care about a closed fuel loop cycle, which basically means also the waste management is not the best in terms of volumes, but the best in terms of ease of process. And finally, there are the molten salt reactors. Now, technically, I could be doing an entire presentation only on molten salt reactors because molten salt reactors are actually a big family. Why do I say that? Because molten salt reactors, it's related only on the coolant, so the molten salt itself. But then there are different iterations of these reactors. Molten salts can be either solid fuel or liquid fuel. In case of solid fuel, we have normal uranium pellets, and the coolant is only molten salt is only coolant. Then we have the liquid-fueled molten salt. This is a very unique type of design where the fuel, again, as I just said, is liquid, and it's the salt itself. And then there's also another difference because molten salts can also be thermal and fast reactors. This also means that we have different designs that are completely different depending on the reactor itself. In fact, what we have here is we have both fluoride and chloride salts. Specifically, fluoride salts are used in thermal reactors and chloride salts are used in fast reactors. Part of my research in my PhD has been done around fluoride salts and how I could use fluoride salts to decontaminate graphite from fission products. Specifically, fluoride molten salt fluoride reactors, the thermal ones, use graphite as a moderator. So the idea was to decontaminate graphite using the molten salt that is within the medium itself. So basically, we're talking about in situ decontamination. One of the interesting parts, especially of the the liquid-fueled molten salt, is that we can have online reprocessing, we can have continuous refueling, so we can have extremely high capacity factors, and also it's extremely flexible. It's probably the best reactor in terms of flexibility and load following. Also here, the temperatures are extremely high, 800 or more degrees Celsius can be reached. The design feature, even though there are different families, I would say any type of molten salt is extremely safe. This is given by the fact that we have passive cooling for thermal reactors. One of the advantages is that mostly, if it's solid fuel, most of these reactors, like the FHR, uses again also triso particles, like in the gas-cooled reactors. So there is the same core frequency damage value. Furthermore, if it's a liquid fuel, it has the possibility of basically being drained out, and that's a very cool feature to have in case of an accident. And then, since they are extremely flexible, one of the coolest part, especially of liquid-fueled molten salt reactors, is that they basically can burn everything that's put into them, any type of fuel. And they're extremely flexible on the fuel source. And again, as I already said, flexible load following. Now, this is more or less all the reactors. There are also other generation 4 reactors, specifically the supercritical water reactor and the gas-cooled fast reactor. I won't go into details with these ones because they are in extremely early stages of design phase. There is none being built, or just only simulations at the moment. So I'm not talking about them because they are still far away, and these ones are the main interested and the one that we have more data on. I would like to leave you with this sentence I really like from Mike Simpson, which is, while nothing is certain, I firmly believe our nation is on the verge of a nuclear energy renaissance. And every year that I'm using this citation, it's becoming more and more real. So with that being said, thank you for the attention. And if you have any questions, I'm happy to answer you. I'll go on the first one so I have some light. And actually, give me a second. I will just turn on the lights. Maybe it's better. Okay. Thank you so much.
Riccardo, I have one question.
Yes, please.
I'm Rob. You can see me.
Yes. Nice to see you. Nice to meet you.
Yeah, nice to meet you as well, Riccardo. Fantastic presentation. Thank you so much for these insights. There's a lot of, I call it inside news. I never knew about it, and you gave me a very clear picture. But the question is as follows.
Mm-hmm.
At the moment, and I'm based, by the way, in the Netherlands, Riccardo.
Mm-hmm.
At the moment, what we see happening on nuclear, that in the Netherlands, they're opening the discussion. So they really want to create nuclear plants, etc., etc. So I think it's a good development for several reasons. But we also see that there are discussions about SMR, and a lot of people think that it's going to be solved in no time. So that's the problem at the moment. So suddenly the discussion after last year is shifting, or not even shifting, it's actually flipping around. Nuclear was not allowed anymore since last year, and suddenly everybody starts talking about nuclear. So could you help me to understand, what do we need to do to choose to speed up at the lowest cost? Because that would be the solutions for politicians to go ahead.
That's a very difficult question, actually. I do not have the answer on which is the lowest cost. I mean, I could actually have an answer, but it's an answer that the public perception usually doesn't like, which is we should go with reactors that already have been built, so as the EPR and so on. That is because...
Riccardo, now you're talking about Germany, yeah?
Yeah.
They closed everything.
That's the problem. All of these reactors are extremely interesting. The problem is there has no been first of a kind commercially. So regardless of what we will choose between these reactors, they will probably cost more than we thought, and they will probably take more than we thought, just because of the specific intrinsic nature of any type of industry, not only of nuclear. So if I had to say to someone today, I want to start building a nuclear reactor tomorrow, I would say, go to one of the big reactor companies and buy one of the ones that are already building, just because those reactors work as fine. The problem that I see, and I'm also very much worried about in nuclear right now, is that there is a lot of advertisement, so to speak. I strongly believe in SMRs and generation 4 reactors, but it seems as they have all the answers that old nuclear doesn't have, which is not actually the case. Specifically, most of the nations who are now interested in SMRs actually are looking at light water SMRs, which is basically no difference, apart from some smaller differences, with old reactors.
Very good that you were saying. It's the same like the belief in hydrogen. Hydrogen is going to create a solution, and now you're saying SMRs are, people believe that SMRs are going to create a solution, but it's a belief, isn't it? So the reality is a little bit different.
I agree. Reality is extremely complex. SMRs, I would say, are part of the solution. When I talk about SMRs and generation 4, and also I would say the naming, because generation 4 seems as, oh, this is an evolution to what we have now, which it technically speaking is, but I see it more as another, as a part of the solution in the grand scheme of things. As I showed you, most of these reactors are more interesting for industrial applications. I'm very skeptical on them being more economical than light water reactors. And what we usually say is light water reactors are extremely good. The problem we had wasn't the reactor, was an industry that was shut down for 20 years. So we lost managers, we lost the supply chain. We also changed midways the regulation, which doesn't help with any type of construction. So we were a little bit in this limbo. I would have, for example, the example of Korea. They never stopped the nuclear industry, and their light water reactors, their new ones, are doing just fine. The point is building an industry and a supply chain that is resilient and strong. Start building light water reactors, and where needed, use Generation 4 reactors, which I would say are at least 5 years away, at least. I'm being optimistic right now because there are some reactors like the HTGR, which already are being built and have been built. So that could be a solution. But still, I would say they're not enemies. One is not better than the other. It depends on the techno-economical problem that that will be posed to them.
Yeah, thanks, Riccardo. Thanks for your answer. Very insightful. Thank you so much. I would like to give the floor to others as well for questions.
Hi, so yes, Dia had a question, I believe, in the chat. He asked, in your opinion, Riccardo, what are some of the obstacles that hinder the commercial widespread of Generation 4 and SM reactors?
Yep.
Well, one big problem in nuclear in general is the amount of capital for research. Nuclear is inherently expensive, and especially the research part. There are still some problems that have to be solved, especially, as I was saying before, material science-wise. It's very difficult from a regulation standpoint also to license new materials. It can take more than 15 years. I'll give you an example. When we want to test a new material, we have to license it based on what we expect it to be the radiation dose that it will get at the end of life. To do so, we have reactors that are specifically made to, for example, give 60 years of neutron dose in 6 years. They exist, for example, the HIFER reactor. But the campaign, nonetheless, lasts at least 6-7 years, plus the bureaucracy beforehand to actually get to do that. So just from a materials perspective, it can take up to 10-15 years just to validate the material. And that is complex because we do not have a lot of high flux reactors that can do the job. And that is important to know. Most reactor vendors, like a lot of startups, already have started licensing these materials. But nonetheless, that is a big point. Then another big problem is regulation. If you see any type of regulation worldwide, it's basically LWR centric. So it's based on what was the technology available at the time. And most of these regulations do not quite fit in the Generation 4 landscape. For example, if we talk about core frequency damage, again, triso fuel particles do not have that. If we talk about leak of coolant for a light water reactor is one problem. For molten salt reactor is a completely another problem. For sodium fast reactors is another issue completely. That is a big problem. I would say also, especially for SMRs, I would also add that the regulation is also a problem in terms, as I was saying before, in terms of standardization and harmonization, because to make them extremely economical, SMRs have to be harmonized. And probably, for example, the licensing process, usually what we do right now is you have to license each and every reactor you build. For SMRs, one approach that could be taken is I do not license the specific reactor, but I license the technology. So once I licensed a specific SMR, and you assure me that that SMR is built always in the same way, then I have to license it only once. Basically, like it's done in many other industries. So I would say mostly it's bureaucratical and material science. And again, a little bit of funding is always a problem, but I think in every industry.
Yeah, I can not agree with you. Okay. So we have a question from one of our members of the community. how much time does it take to reload SMR compared to standard nuclear reactor with capacity of 2 gigawatts, for example?
The answer is it depends. Depends on the reactor. It depends on the burn up. It depends on the design itself. Technically, it could also change the refueling time depending on the same technology, just depending on how you design the reactor. I could say that liquid-fueled molten salt reactors basically have online refueling. So you technically, I would say you are refueling, but technically it's online, so you don't really have a time where you stop the reactor. I think it's quite similar for HTGRs and FHRs that use pebbles, because you can basically shift them around, shuffle them around. Instead, for like, I would say more conventional fuel types, so basically I'm talking about fuel rods, ceramic rods, or metallic rods, I would say more or less the same. Maybe I'm not really sure about the timing. Maybe there's some data and literature about some sodium fast reactors, but I wouldn't expect it to be much different than from a light water reactor.
Mm-hmm. Thank you for your answer. So maybe something else that I would like to know.
Mm-hmm.
How much time will it take for a certain company, for instance, to deploy SMR to the point of actual power generation? And how much time will it take for some other company to deploy a traditional nuclear reactor?
Okay, this is a very difficult answer. There have been a lot of studies on what the answer could be. The reality is that probably the first reactor of any type, new, will take longer than expected. This is true for any type of technology. It's basically called first of a kind. Some studies I've seen were showing around, again, it's very, take these numbers as like a grain of salt because the variability is really high. But they expect, for example, some some advanced reactors to take 7 to 10 years as first of a kind and reach 4 to 5 years in a steady state. Sounds reasonable. Depends on how the regulation also works out. For SMRs, specifically light water SMRs, they say they can build a reactor in 18 months, 24 to 18 months, which is quite low. If they manage to do that, that's really good. But I would say in general, I would not expect, for the first of a kind, regardless of the reactor, I would not expect it to be less than 5-10 years. Like I would say fully commercial one. I'm not talking about research reactors. Those ones take less. I'm talking about full-scale commercial plant, not less than 7 to 8 years, but realistically 10 to 12 for the first one. For like real first one, which kind, and then we can prove like it has been the same for light water reactors. The first ones were around 10 to 12 years, but then you can get up to 5 years with optimization and knowledge management and so on. But these are very difficult numbers, specifically because none of them have been built, so they just can be best guess estimates. But I could be totally wrong.
Thank you very much. I don't see any more questions for now, but maybe I can think of something else. Well, we talked about many types of standard reactors, and some of them that maybe we did not so much talking about them, but for instance, PWR, BWR, AGR, and so on. But what would you say? Can we make them in a reduced scale, and will it be as profitable, or is it only for new types of reactors?
You mean
the
standard reactor?
underscaling?
Okay. You mean the SMRs basically for standard reactors? Okay, well, let's say that I actually really found there are a lot of, most of the designs actually of SMRs is light water reactors, so either PWR or BWR. I really do like them. They have some advantages over larger counterparts. Specifically, they can use more passive safety systems. For example, use natural circulation and so on. Factory build, again, all the design philosophy is the same. They have some advantages. The safety is actually higher. I've seen some data from NewScale that their core frequency damage, I think, is one of the lowest I've ever seen. So they have some advantages. Regarding AGRs, I do not think they're actually planning on ever building one again. So they're just moving to HDGRs. But for light water reactors, there are a lot, like the BWX300 from Mitsubishi, I think, is one of the most interesting one. There's Rolls-Royce, which is a PWR system. There's NewScale, many others. There are a lot of light water SMRs, and I do believe they have a role. Also, for example, SMRs, if I recall correctly, Finland was planning on building SMRs for district heating, which is a really nice, light water SMRs, sorry, for district heating, which is a really nice idea, because one important feature for district heating is that the heat source has to be close to the area where you actually want to use the heat. You can do it's very difficult to do it with a large reactor, but with an SMR, it's easier because you have it closer. So it makes the system more efficient. So that's also another value proposition of same technology, just on a smaller scale. But yes, there's most of the designs of SMRs is actually light water reactors. It makes sense. It's basically a proven technology. So for example, Rolls-Royce, they're basically using every possible system that is used in a large reactor and just scaling it down. This, from a regulation standpoint, helps a lot. Because if you think about it, if I do not have to validate new materials, 10 years, 15 years already removed. So I can just go with what has already been used by the industry. And I'm sure it will work. I do not have to validate it again. And that's a big plus for light water SMRs that the other reactors do not have. That's why I'm sure, like, I can bet on this. The first SMR we will see in Europe is a light water reactor SMR, like 100% sure.
Thank you. We have one more question in the chat. Having listened to the advantages, what are the disadvantages that can be envisaged with SMRs?
Well, one of the main disadvantages, and I will go back to this slide. Okay, this one. One of the disadvantages is that probably they will not cost less. That's one of the disadvantages. Of course, when I talk about cost, I don't mean absolute cost, but I mean normalized cost per megawatt hour. Another possible problem is that SMRs, I will not go deep into how the neutronics work, but let's just take for granted that for a certain technology, the smaller the reactor core, the less efficient the reactor core is. Specifically in how it deals with neutrons. And that means basically the smaller the reactor is, the more neutrons actually go out of the reactor without basically producing fission. So usually the burn-ups are a little bit lower and the activation products are a little bit higher, which basically means more nuclear waste produced per megawatt hour of energy produced. This is not it is, I would say, an issue, a disadvantage that has to be told of. But also, to put it into perspective, it's not that big of a problem. There are some studies that I can link to that actually calculate what is expected to be the normalized waste produced by light water SMRs compared to large scale reactors, and also various advanced SMR types, and what will their waste be. For example, an interesting point, because then talking about different reactors, most of the advanced reactors will produce less high-level waste. But for example, the gas-cooled fast reactor, this one, the gas-cooled reactor is not fast. This is thermal reactor, will produce likely much more intermediate level waste compared to light water reactors. This is because it has a lot of graphite. And that's why also I'm doing a PhD in graphite, because we're actually trying to deal with how to reduce this waste. That is a disadvantage of this particular kind of reactor, for example.
Thank you very much for your answer. So I guess that's it. Thank you for coming. Thank you for being our lecturer
Thank you.
for the ending. And this video will be available at our YouTube channel. So anybody that didn't manage to join in today, they can listen to it afterwards. And I'm looking forward to seeing you again.
Thank you so much for your time. Of course, I will leave you the presentation. There's also my contacts. If anybody's interested to talk even more, please just hit me up. I'm happy to talk about, if anything. thank you so much, really, for your time. And good luck with this project. Amazing project, really.
Thank you.
Thank you again for having me.
Bye.
Thank you, Riccardo.
Thank you so much. Have a good evening, you all.
You as well.